Hello, and welcome to another lecture in this course. So today we're going to look at the inverse function theorem and automorphisms in general, the biholomorphisms. And we're looking at subsection 2.2.3. All right, so suppose that I have two open sets, U and V in C. And let's suppose that I have a holomorphic function from U to V that is bijective, right? So the inverse exists, and the inverse is holomorphic. Then we say that F is a biholomorphism, and then we also say that U and V are biholomorphic. They're kind of equivalent as far as holomorphic functions are concerned, right? So if you understand the function theory on U, you understand the function theory on V and vice versa by just composing. So basically, if you want to study the function theory on some domain, you can just study it up to a biholomorphism. So it's really a change of variables, right? So surprisingly, this is something I will see later. This, this hypothesis that F inverse is holomorphic is unnecessary. We'll prove later that any bijective holomorphic function is actually biholomorphic. It's weird, but yeah, it's one other weird thing that you get from holomorphic functions. But that's gonna come later. We need a lot more machinery for that. So, all right, if U is equal to V, then we call F an automorphism. Right? And should remark that the word automorphism gets used in sort of any context when you have, a function between two things that preserves some sort of between two things, between the same thing, thing to itself that preserves some sort of structure. A lot of times people just call it an automorphism. So it's basically, in this case, we mean a holomorphic automorphism of of open sets. And the set of automorphisms which we'll write out or out, however you would pronounce it, the set of automorphisms of U, and that's a group under composition. So the group operation is composition, right? And that's an easy exercise that actually is a group. So it's usually called the group of automorphism or the automorphism group. Now, traditionally, a biholomorphism is called a conformal mapping, and then U and V are then called conformally equivalent. This, you see this a lot. Unfortunately, it's sort of it has a different meaning in several complex variables. So once you do complex analysis in more than one variable, you wouldn't want to call it a conformal mapping, conformally equivalent. So saying biholomorphic is definitely okay. So it's with that proviso, they're the same thing. All right. So as an example, for example, the Cayley map, that takes the upper half plane to the disk and is invertible, right? The inverse is also an LFT, right? So it's a holomorphic function with a holomorphic inverse. So this C, if I restrict it to H, is biholomorphism, right? And H and D are then biholomorphic or conformally equivalent, if you want, in the traditional wording. Now, another example is C, and I look at automorphisms. And actually, all the automorphisms actually look like this, but right now, as an example of an automorphism, yeah, I mean, for any a, as long as a is not 0, az plus b is an automorphism of c. All right, so suppose f is a biholomorphism. So if f is a biholomorphism, it has a holomorphic inverse. So this equation is true. I can differentiate both sides, and I will get this complicated mess, right? So it's the derivative of the inverse evaluated at f of z times f prime of z, right? By chain rule, right? Now that means, in particular, that the derivative is not 0 for any z, right? Because 1 is equal to the derivative times something else. So the derivative can't be 0. Also, and let's set w to be the f of z for simplicity. Then what we have, I can solve for the derivative of the inverse and the derivative of f in terms of the other, right? So the derivative of the inverse is 1 over the derivative of f at the corresponding points, right? And the same thing over here. I mean, it makes sense because, f inverse, the inverse of f inverse is f, right? So this is symmetric, right? So I should get, both of these. All right, so let's consider a holomorphic function f. Its real derivative is writing it as a function of u and of x and y, and writing the function as u plus iv. And then let's look at the determinant of this. So that's the Jacobian determinant, right? And that actually has a nice formula, right? So first, well, let's just compute it. It's this times this minus this times this, right? So I'm writing here just a formula for a 2 by 2 determinant. Now, and this is true for any holomorphic function, not necessarily biholomorphic one, right? But holomorphic, so I can use the Cauchy-Riemann equations to replace these guys, and I get this bit here, which is, right, I know that taking the x derivative, for example, right, if I have a holomorphic function, taking the partial x derivative, well, that gives me the complex derivative, and what I'm doing here is I'm computing the squared norm of the derivative, right, the modulus squared of the derivative, right? So that's actually kind of a neat computation, right? If you have a holomorphic function, the Jacobian determinant of the real derivative is modulus squared of the complex derivative, right? In particular, what it means, and there's other ways of thinking about it, why this is true, but df is invertible if and only if f prime is non-zero, right? By the way, something that we've also proved, that it's just a remark, we've now proved that holomorphic functions preserve orientation. We haven't really talked about orientation. We're not really going to talk about it in this course, but yeah, that's what we did, because the determinant of the real derivative is always positive. Well, unless it's 0, but this is always non-negative, at least, right? So if f prime is never 0, then you have something that preserves orientation. All right. So let's look at the real inverse function term for continuously differentiable function from R2 to R2. And that says that if, and here we need continuously differentiable, that's necessary for inverse function term. If you have the derivative is invertible at some point, then f actually takes a little neighborhood of that point bijectively to another neighborhood, and the inverse is continuously differentiable, and the derivative of the inverse is the inverse of the derivative, right? So that's what the real inverse function theorem from vector calculus says, right? Applies to R2, right? Well, I apply to any Rn, really. Okay. Now, if a 2 by 2 matrix, 2 by 2 real matrix represents a complex number, then its inverse, the inverse of the 2 by 2 matrix, represents the reciprocal of that complex number, right? So if it if a matrix represents multiplication by a plus ib, then its inverse represents multiplication by 1 over a plus ib, right? Okay. So in the theorem, in the inverse function theorem, if f is holomorphic, then so is the inverse, right? Because I have, well, if the derivative represents a complex number, its inverse also represents a complex number, namely the reciprocal. So we can just state the inverse function theorem. We just write down the inverse function theorem for real functions. We write it down in terms of holomorphic functions. What does it mean for holomorphic functions? So suppose that I have a holomorphic function defined on some domain or some open set, and we have some point in this set, and the derivative of f at p is non-zero. Now we're going to assume, I'm going to say a little bit more about this in a little bit. We're further going to right now assume that f is continuously differentiable, right? So that means that all the partial derivatives exist and are continuous. Then there exist open sets v and w, right? V is just like the v from here, right? It's a neighborhood of p, and w is the image of v under f. The restriction to v is injective, right? It's actually, well, of course, it's onto w by definition. So it's a bijection between v and w, and hence there is an inverse. Let's call it g, right? And right, this just says that there is an inverse, right? So it's an inverse of f, right? On v, right? And furthermore, so that's already saying something, right? I mean, that's already saying that, right? For example, this is an open set, right? And that's not, and that f is injective in a neighborhood, right? But furthermore, this inverse, right, is holomorphic, and its derivative is given by this formula, and it's precisely this formula over here, right? I mean, that it's holomorphic, well, it's continuously differentiable, and the derivative represents multiplication by a complex number, right? Therefore, it's holomorphic, right? So that's what we get, and we know that the derivative of the inverse is 1 over the derivative of the function itself, right? Because that's what this says, right? All right, so that's the inverse function theorem. It's basically just like the inverse function theorem for real functions. Now, we will later prove that this hypothesis is unnecessary. Any holomorphic function will automatically be continuously differentiable. Right now, we haven't proved that yet, so that's why it's there. But we'll prove that that's not necessary. Every holomorphic function is going to be continuously differentiable, right? You can even prove, you can give a, later on, once we have more machinery, you can give sort of a more, complex variables proof of the inverse function theorem, where, of course, this hypothesis wouldn't be there either, right? So, but for that, we'd need more machinery. Right. Now, just because the derivative is never zero of some function doesn't mean that it's globally bijective, right? I mean, the simplest example is the exponential. The derivative is just the exponential is itself, and that's never zero. But it's not one-to-one, right? It's I can find lots of points that go to 1 point, right? Now it is locally near any point I can find an inverse, right? But not globally, right? So locally I can find, well, the inverse is going to be the complex logarithm. So locally I can find a logarithm, but there is no logarithm. No sort of globally defined logarithm that's really because of this, right? Because there is no, it's not a one-to-one function. Unlike for the real, in the real case, right? The real exponential is one-to-one. It's maybe not onto, so the real logarithm is only defined on the positive numbers, but yeah, right? It's well defined. Here, it's not, right? But locally, we can always invert e to the z, right, by this function, by this theorem. Now, another thing that there is an interesting remark here is that locally, if I'm not worried about what these neighborhoods are, there's lots of local biholomorphisms. Sorry about it. Because there's lots of functions with non-zero derivative at any particular point, right? Lots of holomorphic functions. I mean, there's even lots of polynomials with this, right? However, if you fix the two open sets, there's generally very few biholomorphisms. A lot of times there's none, right? If U and V are not biholomorphically equivalent, then there are none, right? And even if there are some, there's actually generally very few. For example, if both of them are D, and we'll prove this later on. So if I have an automorphism of D, then it actually always can be written in this form, right? Where theta is real and A is a number in the disk. Similarly, if it's an automorphism of C, then it's always of this form, where A is non-zero and A and B are just complex numbers. And comparatively, these two sets actually have a lot of automorphisms, even though they have very few, right? I mean, it looks like there's a lot, but right, because you can vary these constants, but that's very few. That's very few functions, right? I mean, if I'd look at real diffeomorphisms, right? Real differentiable function with real differentiable inverse on D to D, there's just insanely many, right? It's impossible to say anything about this set, right? But for holomorphic ones, there's very few, right? And for example, if you take a disk and sort of remove sort of 3 generically placed points, then only the identity is an automorphism. I mean, there's always an identity automorphism, right? If I'm talking about an automorphism, right? So we don't have the machinery to prove these statements, but we will later on. So there's going to be a whole section on the automorphisms of the disk, right? All right. So next time we're going to start looking at power series. So yeah, see you next time.